All right, so this is the lecture 3 of moment of inertia. Now we are going on to the proofs of the two theorems that we said. Fine. So if you recall, the first theorem was theorem of parallel axis, right? So now before we go into the proof of this parallel axis theorem, let's just take a moment to discuss something basic. Fine. 2 points. One, if suppose that this is the plane, let's say, which plane? The xy plane, let's say, fine. And you have over here a line, fine, which is perpendicular to the xy plane, fine. And there is a point over here which has coordinates of x naught, comma, y naught, comma, z naught, let's say, fine. Now, how much do you feel is the distance of this point from this particular line? What is the distance do you feel? So what we can do is construct a plane which is parallel to this particular plane. You can imagine how it is. Okay. It would be parallel over here, this way, this way, this way, this way. Fine. Now, whatever is the distance over here from this line to this particular point in that plane is the same distance that it would have over here also. If you were to drop it vertically down, project it on the xy plane, and these two distances would be exactly the same. This is nothing but the projection of this point on the xy plane itself. Xy plane has what coordinate as 0? Z coordinate as 0, which means that over here these coordinates are going to be x naught comma y naught itself. And therefore, if this is the x-axis and this is the y-axis, what is the distance of a point having x naught y naught from this particular axis over here? Let's say that this is the origin. Can we say that this distance would be root of x naught square plus y naught square? And therefore, this distance over here would also be the same as this particular distance. Fine. The idea is clear, right? Why? Because this particular plane is perpendicular to the xy plane, which means that this is parallel to the z-axis. Fine. And it would be true for any other line also. For example, if you had a line passing over here this way, right? Let's say that this is the line over here. Fine. And this one is also perpendicular to the xy plane. Fine. Now, how much would be this particular distance over here? This one would also be equal to this distance over here. And if we know the coordinates of this particular point over here, you can use the distance formula to find the distance. Suppose it has coordinates x1, comma y1. So the distance would be root of how much? Square root of x naught minus x1 the whole square plus y naught minus y1 the whole square. This would be the distance between the line and the point P also. Fine. This is point number 1 that we have to make a note of. Fine. The other point is that the definition of the location of center of mass. Now, how do you define the center of mass? For example, the x coordinate of center of mass. What is that? Is it not defined in this way? X com is equal to integral of dmx divided by integral of dm. And what if the x coordinate is chosen? The center of mass is chosen as the origin. That means the x coordinate of center of mass would be the origin. That means it would be 0, right? If x com is at this location, 0, x com, y com, and z com also, let us say. Why? You have freedom to choose the axis. Fine. Okay, these 2 points alone we will make a note of before we move on to the proof of this parallel axis theorem, right? Okay, proof of what we discussed in lecture 1. If you have not seen that, you can check that out. Right? So over here, and we are going to uh, take some convenient steps. Fine. One, object is fine. Could be any object. This is the center of mass. This is the axis which passes through the center of mass. And this is the other axis over here. And this way it is, let us say, fine. Okay. Now we are going to select, for our convenience, we are going to draw the XYZ axis in such a way that the calculations becomes easier. Fine. Choice of axis is up to you, right? There's no problem with that. So let's take the center of mass itself as the origin. Let's take this particular distance as d. We are going to take over here in this direction to be the x-axis, this as the y-axis, and this particular axis over here of the center of the mass as the z-axis this way. And this axis is parallel over here to the z-axis. Fine. That's clear, right? So which means that this would be the negative x-axis, correct? The coordinates of this point over here would be what? Minus d, 0, comma 0. Fine. Just a what do you say? It's just a way, right? Just a convenient way. So now let's select on this rigid body a point over here where the mass is dm and the coordinates are x. Let's call it as xi, yi, zi. Fine. Fine. I have a question for you. What is the distance of this element from this particular axis, which is parallel to the z-axis? Can you tell that? What we discussed earlier, we can do that. This is the axis, and this is the point over here. We want the distance of this point from that axis. Use the formula, the distance formula. Fine. So therefore, over here, we notice that since this axis is parallel to the z-axis, you can project this particular point over here, call it as the P point. The x coordinate is not going to change. Y coordinate is not going to change. On the xz plane, z coordinate will be 0. And now you have this particular point over here. So the distance between the axis and that point is nothing but this particular distance over here, this one. The distance formula says that this is equal to how much? Square root of xi plus d, the whole square. Then what is that? Plus yi square. And therefore, what would be the moment of inertia of that element about this axis? We call that a di. We let it dm multiplied by the square of distance. What is that? Xi plus d the whole square plus yi square. Fine. And let's open up. Let's open up the bracket term. What do you get? Dm xi square, correct? Plus dm into 2 into xi multiplied by d, correct? Plus dm multiplied by d square plus dm multiplied by yi square. Fine. So now let's integrate on both the sides. This way, this way, this way, this way. Let's combine these two terms over here, this one and this one, for a specific reason. So this becomes equal to dm multiplied by xi squared plus yi squared. And this one is 2D integral of how much this term over here is dm multiplied by xi, okay, plus this is integral of dm multiplied by d square itself. So what is this one? Dm multiplied by xi square plus yi square. Is it not the moment of inertia about the z-axis? Yes, it is. This is nothing but the distance of this particular element over here from this particular axis over here, this distance, square of that. Since this one is xi square plus yi square. So you get this as equal to how much? You can now write directly this term is I about the center of mass axis and the one which is parallel to the I axis. Fine. What is this term over here? Integral of dm into xi. Is it not this quantity over here? Integral of dmx. And xi is the variable quantity over here. Right? I is the ith particle, I1, I2, I3, and so on, right? Which means that it would give us xcom multiplied by total mass if you take this term to the right hand side. But what is the x coordinate of center of mass for this problem? We have taken the center of mass as the origin itself, which means that this term, this 2D multiplied by dmxi is simply equal to x coordinate of the center of mass multiplied by the total mass. Plus, what is this last term over here? D is a constant. It's a distance between the two lines. So you can write it as d square only. Integral dm is nothing but the mass. Fine. And this term will become 0 because it's the origin x coordinate. It leaves us with I as I com plus md square. This is your proof of the parallaxis theorem. Fine. So any object is there. All you need is one line which is passing through the center of mass. And you can find out the mi about any other line which is parallel to this particular axis. Fine. This particular I value is given as this particular I value plus mass of the entire rigid body multiplied by the square of the distance between the two axes. Fine. This idea is perfectly clear. Excellent. So now let's move on to the next proof, the perpendicular axis theorem. Perpendicular. What is that? As the name suggests, the axis must be perpendicular, right, instead of being parallel. And these are only valid for laminar or planar structures. Fine. So let's select over here a planar structure. Maybe it's any kind of shape it could be, but the mass must be confined in one plane only. Fine. And for convenience, let's take this as the x-axis, the y-axis, and this one as the z-axis, the one which is perpendicular to the x and y. Fine. Let's draw it this way. It would be convenient for us this way. Fine. Okay. So now let's select over here one element which has coordinates of how much? Xi, comma, yi. And since it's the xy plane, so therefore the z coordinate is going to be how much? Z coordinate will be 0. So therefore, how much is the moment of inertia of this particular object over here about the x-axis? We notice that small elemental moment of inertia about the x-axis is nothing but dm multiplied by the square of distance from the x-axis. From the x-axis, the distance of any point is sum of the squares of the other two axes taken under root. That means yi square plus zi square, which means it is simply dm multiplied by yi square, your dix. Fine. And what about the diy? Similarly, it would be equal to dm multiplied by xi square. Fine. Let's add these two. So what does it become? Dix plus diy is nothing but dm multiplied by xi square plus yi square. Fine. But what is xi square plus yi square? But not the distance from the origin. And if this is in one plane, it means it's the distance from the z-axis also. Fine. So therefore, it simply becomes the value of diz. So dix plus diy is diz. On integrating, we observe that it is ix plus iy is equal to iz. Fine. Now this is valid. So what are the conditions for which it is valid? Number one, object must be in the same plane. Fine. Object in plane, one plane. Number two, ix and iy are in that plane. Fine. Number three, iz must be perpendicular to that plane. Fine. If it satisfies all of these conditions, then it doesn't matter whether the origin or the point that you're selecting is in the is present in the area of that object or outside. Doesn't matter. This relation is going to hold. Ix plus iy is iz. For example, let's say that you give a small example. This way it is. Fine. The point B. This is one axis which has moment of inertia of I1. This one is perpendicular to that and in the plane over here. Fine. And this is the axis which is perpendicular to the plane. I1 and I2 are in plane MI values. I3 is perpendicular. What's the relation between I1, I2, I3? That's all. I1 plus I2. Fine. These were some of the short proofs. And that's it. That's it for this particular class. Thank you for attending. Thank you.